Welcome to the first lecture on simultaneous localization and mapping. We built so much in this course so we can talk freely about SLAM. SLAM stands for simultaneous localization and mapping. We learned how to do a state estimation using a range of filters that we covered. We saw them as instances of each of them was an instance of base filter in the narrative that we built. Typically, that filter consists of a prediction step and a correction step. And then we moved into the optimization. We talked about how to do frame-to-frame alignment of images, RGBD images, and point clouds. We used particle filtering for localization in particular, and then we talked about some mapping algorithms. Today, we want to put everything in one framework and talk about how to do both localization and mapping at the same time. To do localization, we need a map. To do mapping, we need localization. In a SLAM, neither of them is given to us. So we want to build a model of the environment, a map, while we are localizing with respect to some initial frame that we decide as time moves forward. In this particular lecture, we will focus on graph SLAM. Historically, there are three main paradigms of SLAM in the literature. The problem initially started by looking into Kalman filtering based SLAM and its variants, information filter, sparse extended information filter. Those were categories of SLAM methods that were using filtering-based method. And as we discussed in the filtering methods, we marginalize past information. Every time we predict, we marginalize in the Bayes rule. So we don't keep the history. We only estimate the latest, let's say, robot pose. So one particular problem in Kalman filtering-based SLAM is that we need to work with landmarks. And every time when we track a set of landmarks as our map in the state, we need to solve a data association problem, meaning we need to know what are the correspondences between a set of observed landmarks and the map we maintain in the state. Typically, landmarks might not come with a signature that we know correspondences, so we need to do some sort of a statistical test to find out what are the correspondences. And that process is prone to outliers and mistake. And the filtering process is not very forgiving for such mistakes, because if you make a mistake, you inject outliers, and we never go back in time to correct past mistakes. We only linearize once, incorporate information, and move on. So in that sense, it's a framework that does not allow for dealing with outliers arising from data association. Then particle filtering came along. Fast SLAM is a version of that. That we build a map, can be occupancy grid map or landmark maps, and each particle is a hypothesis for the robot pose, and we track a separate map for each particle. This method works well, and still some versions of it called G mapping, for example, or fast SLAM algorithms are in use for 2D robots moving in indoors usually. However, the problem we face here is the scalability problem. On top of that, typically particle filters are also within the filtering class, although they can be implemented as smoothing, but that will make them only more expensive. So tracking multiple hypotheses and building a world model for every particle becomes quickly intractable. So in practice, we might end up using a few particles for solving the problem. Then the next generation of these methods was to move on to a smoothing framework. And that was motivated by the fact that the SLAM problem admits a particular structure that makes the problem sparse. Even though it's larger scale, we keep a lot of data history as the robot navigates through the environment, but the problem ends up being a sparse linear systems that we wish to solve. So it was counterintuitive that if you get rid of the history, it makes the problem harder to solve. If you keep the history, although you're dealing with more data, but it makes it easier to solve because we enjoy the sparse structure of the SLAM. This was discovered in an iconic paper. It's called exactly a sparse extended information filter that won an award in Transaction on Robotics. That was in the context of extended information filter, and the observation was that if we keep robot poses and connect these poses across time by establishing some constraint, then we see a sparse structure. Now, when we go to graphical models, we see that explicitly already in the Jacobian that we construct for the least squares problem. So today's the main paradigm for SLAM is graph SLAM, right? So the other two are history, and we're going to focus on SLAM. Tomorrow, we don't know. Maybe there will be other methods. So the graphical models for SLAM, it means that we use techniques in the context of probabilistic graphical modeling to formulate the problem. Although there are many ways to perform inference in a graphical model, we make a particular assumption that the noise is Gaussian, and that will lead to a least squares problem. So we will not look into a general inference methods on graphical models. It is possible, but that will not give us solvers that can operate really fast by solving least squares problems. As we discussed, least squares is a problem for solving an overdetermined system of equations. We have more observations than the number of variables, which makes our matrix tall and full column rank. We discussed this in the optimization lecture. And then we're going to apply this formulation to our SLAM problem and solve it using least squares. So the problem is how to formulate the problem. Once it's a least squares problem, I expect you to know what to do at that point. So how to formulate the problem? Imagine a robot is navigating through an environment. If we record robot poses at discrete time steps, then you might label them using these blue triangles. Then you can think about temporal constraints between any two robot poses that we wish to track. And this way of tracking the robot pose will give us, of course, a discrete time trajectory of the robot. For example, you can call this your node at time t0, t1, t2, and so on. So this will be a trajectory. What are the examples of this constraint that we can add? Based on everything you learned so far, how can we establish a constraint between two robot poses at two consecutive time steps? A transformation. Where does it come from? Poses. Well, where does it come from? We need a sensing method to get that pose. You're right, it's nice to have maybe a pose, right? 2D or 3D. But where do you get it? Odometry. Using maybe wheel encoders, or what about IMU? Could be IMU, could be wheel encoders. Can we use cameras? We learned RGBD visual odometry could be from camera. Could be from ICP, could be point cloud registration. So in general, it can come from a variety of sensing modalities. And that's what makes it compelling, because now we're talking about a generic framework for sensor fusion. we can combine heterogeneous types of sensors by different techniques of registration into one framework for state estimation. So although it's an abstract idea, but you do have a specific knowledge how to get such constraints. Now, if we just rely on temporal constraints, the robot will eventually drift. Imagine every time that you are using will encoder to accumulate delta pose between two nodes, or every time you register two RGBD images. Maybe there is a small error, which is very likely. It's unlikely you get the perfect solution in practice. The accumulation of all of these small errors over time will be a large drift. So the robot will necessarily drift. However, if you can revisit, for example, the robot is coming back to the same area, if you have a way to recognize and establish constraints between previously visited areas or nodes in the graph, we get a special type of constraints. These are not constraints that are temporally sequential. These are called loop closures. As you see, the robot is closing a loop. Loop closures add information that we need for removing the drift from the trajectory. The more constraints you add to this graph, the more likely we have a better answer. Theoretically, that's the case. In practice, of course, we need to be careful. Maybe it's noisy, outliers, local minimum for the solver, all of them, initialization issues. These are problems in practice. But theoretically, more information, more edges to make the graph more connected, it should be better. Although there are research showing that there are diminishing return in how many edges you want to add. Theoretically, again, it's better to add more, but at some point there is a diminishing return as well. There's a structure in this graph, it's called, that admits a submodular information gain. That's part of the research in Islam, and it's possible to select a subset that you have some minimal loss of information. That's just a side note. So the idea is that you build a graph. You imagine how the robot or your sensor is moving in the environment and represent the problem as a graph. And this graph is abstract enough that we can show different types of robots and sensors using just nodes and edges. So every node corresponds to your variable. That can be the robot pose, or it can contain the velocity of the robot or bias variables. In general, that's the node represents your state variable. The edge is some sort of constraints between the state variables. If you remember from how we formulated the RGBD registration, that's one type of edge. It's a measurement model that links two poses to each other through some measurements. So the core idea is that build a graph by establishing these connections, then formulate a problem by minimizing the error between the estimated variables and observations. Then by minimizing them, we should recover the entire trajectory. For example, imagine a robot is navigating in this 2D environment. If you use odometry, for example, to build an occupancy grid map, you might expect to get something like this, which is not very useful. The map is inconsistent, as you can see. All the walls are overlaying on each other, and it's not very useful for navigation. Now, as the robot is navigating, we construct the graph. There are potentially many nodes along the way, connected by odometry. And as the robot is re-observing same areas, we see we have a lot of loop closures. These are connections that the robot is establishing, in this case, using a 2D laser rangefinder by registering observed point clouds at previous time steps and the current time. So once you build this graph with many edges, this is the graphical representation of the problem, which is exactly what you've been working on in your homework 7. The Intel dataset that you're processing is something that is built just like this. However, the raw data is processed. You are using processed data that was used in some front end. You're working on the back end part when you are given all these constraints and nodes. So there's a part of the problem that was solved for you in your assignment. Now, ideally, when we solve the problem, we expect the trajectory to go back to its consistent form. When you have the trajectory, then you can use the trajectory to build the map. And then hopefully that map is consistent. So, although it's simultaneous localization and mapping, the idea of map is very abstract and somewhat vague because there's a lot of freedom whether you're actually building the map at the same time you optimize the trajectory or you're using a map representation that is built after solving the localization problem. We'll talk more about different types of mapping, but in this case, it's a pose graph. So the pose graph, which is a particular type of a SLAM, where all the constraints are relative measurements between robot poses and all the nodes are robot poses, it solves the localization problem. All the map information is converted into pose-pose constraints. So the current theme or narrative that you see in graph SLAM in literature, in the most abstract way, you can present it like this. Typically, we receive raw data from sensors. The raw data can come in form of point clouds, IMU signals, wheel encoders, monocular images, RGBD images, and so on. There is a front end. The front end is responsible for constructing the graph. There's no unique way, depending on the sensor or data that you process or how you want to combine them to get better constraints, you might come up with different ways of formulating the problem. And that is precisely the topic of research of many papers you see. Different ways of realizing this framework or processing data or inventing new factors or measurement models for the backend is the topic that people still publish on it. Once the front end gives you edges and nodes, then the backend is typically just responsible for graph optimization. So there is a need for an inference method in the backend. Optimization methods, by the assumption that we will make, are very attractive because it makes it very fast and we can run it online. However, there are other possibilities as well. You can always look into broader contexts of inference in graphical models, and they should be applicable. Although, as far as we understand, we cannot make them real time for any interesting problem that we want to solve for robotics. So what does this mean? Now, by the way, the interplay between front end and back end, it's not super clear here that whether the back end is communicating some data to the front end or not. These are all up to debate. Whether it should be like that, ideally all the modules will communicate and they are integrated, but to what extent that's possible, you need to look into different ideas and see what's the best practice at any time. In the simplest way, of course, they're disconnected. The front end builds the graph, passes to front end, you optimize something, and then you might use the trajectory to do some initialization in the front end. But that's never revisited in the sense of regenerating those constraints in the graph again, right? Imagine you also want to go back in time and redo some of the work that front end did. That's more unusual to see in the literature. So this interplay is not well defined and is part of basically problem solving. To get constraints, you can think about two main approaches. One is that to use, for example, if it's in the context of point cloud registration, you might want to use the most recent point cloud you observe from the sensor with another point cloud observed by the sensor in the past. So that will be just frame-to-frame registration. Or maybe you are building a map, and then you want to use the map model as your world and register the most recent frame to the map. So this is another idea, because now I'm using the reconstructed scene or the map, whatever representation it might have, to guide my problem solving in the sense that I want to find out new constraints in the graph by building on the partial model that I have at any time. Now this idea tends to work better frame to map registration. However, it comes with challenges in practice. Frame to map registration is not always easier depending on what method you're working with. For example, for point cloud registration, your point cloud from the sensor might have a different density from your map, which is the accumulation of multiple frames. And many point cloud registration algorithms cannot deal with that. You might need different tuning, different parameters, and so on. So it's a good idea, but in practice, it's not guaranteed to give you a better solution. So everybody is comfortable with this narrative of front end, back end?
Can you explain again how the graph construction, like it seems that the graph construction will still drift a lot, yet the robot will still be able to navigate fine through its environment, even without the mapping from the graph optimization. Since that happens afterwards, it may not be connected, right? So I guess, can you explain again why the map part is so useful to have if the robot can still navigate through the environment without it?
You're asking if the robot can navigate without having the map.
Right, because in the, I guess, data set that you showed us, like the odometry still drifted a lot. In that data set, was the robot driving autonomously, or was it?
Good question. So you're asking if I need to solve a SLAM to have this map so that I can navigate, how can the robot move around to collect data to begin with? So that's a very good observation. So the data is collected by driving the robot manually. This problem is not active. The problem of a state estimation or perception, it is passive. The motion commands are given. In this case, for example, you are driving the robot around this room. You collect data. Maybe offline, you process it to reconstruct the scene and solve the localization problem. Or even if it's online, you are driving the robot. So the robot is not autonomous, which is less exciting, obviously. So if the robot now is going to be autonomous, That means it needs to make decisions for acting. There is no manual intervention for moving the robot. In that case, the problem becomes active, and that might be known as active localization, active mapping, active SLAM, exploration for mapping, and many other names. So the problem is active when you have control over actuation. In that case, you do need a lot more to help the robot to move around. For example, you might want to build a local map. Depending on what is your exploration algorithm, you might need to know the global knowledge of the environment at any time, or at least partial knowledge of the environment with global localization, or you might just rely on local information to move around. The early algorithms, they, for example, wall following, right? Find a wall, just move along the wall, hope for the best, right? Obviously, the robot doesn't know where it's going, but that allows you to explore in some sense. And maybe it might not be a bad idea for some initial phase of the exploration. Another idea is that start here, build a map. We can build it without moving because your sensor is seeing some areas near the robot. There's a method called frontier-based exploration. Find the boundaries between these known part of the maps and gray area, unknown. Then the robot knows that if it moves to the boundary, it can expand the map. So maybe choose the nearest one. That's the nearest frontier exploration, the most basic standard autonomous exploration method. However, as you move, you notice already that you need to maintain good localization. So you expand the map and keep the map consistent, because if at any time the robot localization becomes inaccurate, or for example, you detect the loop closure, now the SLAM fixes the graph from this to this. Whatever map you were tracking and locally you were trying to plan is not valid anymore. So you need to rebuild the map. And it is a problem. How do you know when to rebuild the map? Redoing everything from scratch is very expensive. Partially updating it might not be easy, because the statistical algorithm we had was not allowing us for a flexible structure to update and downdate the map necessarily, right? So each of these problems are challenges in practice, and there are some work in literature on that, but there's no answer that ends the problem as a solution. There are good ideas in literature. So in this case, the problem is passive. Somebody is moving the robot, which is the same assumption in localization. The control actions were deterministic and given. We never assumed we have control over them. Does that answer your question? So the trajectory is a sequence of robot poses, x1, xn. For example, here you might assume xi is in SE2. If it's a 2D robot, you have 2D position and orientation of the robot. Now, as the robot moves in the environment, you have an odometry constraint between node I and I plus 1. Maybe from the wheel encoder, you know your delta x, delta y, delta theta movement, and then that will give you an SE2 constraint in the graph. So you could basically put this in an SE2 matrix, and that will give you a measurement, as we saw it in the post graph example in the optimization lecture. This is a temporal constraint, right, between I and I plus 1. To establish a non-temporal constraint, can we still use odometry? Can we rely on tracking of the robot? Yes? No?
That's the issue with drift, right?
No, regardless of the drift, can we establish non-temporal constraints by just tracking the robot?
What do you mean by just tracking, like, through sensors? Through, like, odometry will just give us...
Odometry, I'm walking, I'm counting my steps. Can I establish a constraint between history from what I observe now? No. It's not possible, right? Because the images I see, let's say I'm solving visual odometry, I'm walking, I can track it at each step using vision. That's one relative pose. I can count the steps, that's another constraint, which is, by the way, there's no limit. You can have many odometry constraints between two nodes. But to have some sort of evidence that what is the relationship between my pose here and 10 steps ahead here, I need to look back in time, whether that's a map or the exact image I observed, to establish some sort of evidence-based constraint. And that evidence-based might come from a constraint between, for example, two images, right? Maybe I store raw measurements, then I look back in time, try to establish a constraint. Or maybe I'm tracking a map. Based on where I am, I try to establish constraints nearby. So this is not a problem that we can solve with using temporal data. In particular, at time step I, we might have observed a point cloud, a measurement of a corner of a room that's like this. And at time step J, maybe I observed the same corner, right? Maybe the robot moved around the room, came back to the same corner. Now, this node xi and xj are not the same place, right? Maybe xj is here. However, the sensor is observing the same area. There must be a relationship between these two, given the overlap in the sensing. So that's the goal. For example, I can use point cloud registration. Maybe I use ICP to register these 2D point clouds. That will give me a relative pose. That's the constraint between xi and xj. So conceptually, this is how we get loop closures. And in practice, so the odometry, the way it's related to nodes, because xi is my state variable. I want to estimate it. xi plus 1 is also my state variable. I want to estimate it. The edge is some sort of measurement, u. The way they are related is that xi inverse times xi plus 1 is the relative movement given xi and xi plus 1. So if I have this relative movement from any sensor, whether I'm you, wheel encoder, point cloud, camera, this constraint is true, right? It must satisfy this relationship in the graph. And that is exactly my measurement model or factor model. When it's observation-based, it's not coming from temporal tracking, in the context of having a state variable as poses, it's the same thing, except we're not talking about I and I plus 1. You see I and j. J can be any other node in the graph. So that's the difference. You might say, okay, this is my, I'm going to show it with Z. Maybe you get this from a camera. Maybe you extract features in 2 images, you run ransack, you find a transformation. That will give you the Z, the relative transformation. So based on observation, evidence, you generate this constraint because the sensor doesn't lie. But we do not know the value of these variables. Then we formulate an optimization problem based on sensor data. We find a trajectory that minimizes some notion of error.
When you don't get any like observation edges, you have n-1 edges, does graph SLAM devolve to like the same performance as another SLAM solving solution? Like when you don't get any loop closure, is it the same theoretically as like a Kalman filter or something else?
That's a good question. The question is, I'm going to use this slide because we have plenty of white space. The question is, if we never get any loop closure, is this the same as Kalman filter? It is not. It's not as good as a SLAM because this is still odometry. But it's odometry in the sense of smoothing. I'm still trying to use temporal constraints to track the robot. So in the sense of odometry, it's a better way of doing odometry. And you might choose to do it over a window, so it's a window tracking. The filtering, we never, let's say Kalman filter or particle filter, we marginalize the history. We only estimate the latest one. In the prediction stage of base filter, we integrate out. Now that integral is not something in closed form. We have a universal solution to it. For Kalman filter, given the Gaussian distribution, we ended up having that update for the prediction and the covariance update. For particle filter, we were just sampling. It wasn't even a parametric calculation. Nevertheless, we are concerned with this latest variable in filtering. Whereas in smoothing, we look at the history. So in this framework, maybe this answers your question, you do get what you were getting out of Kalman filter. If done correctly and carefully, you can cover that case as well. The general graphical model can model something like a Kalman filter as well. Okay? Now, when I say graphically, so you need to be careful about the geometry, right? Because you never see something like a Lie group treatment of graphical models for inference in Kalman filter. That comes from completely different literature. But it is possible to unify them once you realize it correctly using techniques we learned here. Okay? In the linear case, it's very easy. Linear Kalman filter, it's just, in your homework you had that. It gives you the same answer as maximum posteriori and linear least squares. You could do recursive least squares. It will give you the same answer, right? In the nonlinear case, it's hard to say because keep the history, they will affect each other. Get rid of the history. If you didn't do your best at the time of linearization, obviously we lost something, right?
What if the loop closure detects the wrong feature? So for example, in the previous couple slides, we have xj and xi.
Mm-hmm.
And what if I identify the wrong feature? What would be the issue?
So the question is, what if the loop closure is wrong? We somehow fall into a trap of outliers and establish a wrong loop closure. Now, that is, in this case, we're talking about the concept, right? That will be the next step. Now, you want to solve it in practice, you have to deal with outliers. That is a problem in general, because if the system is not robust, it will break down easily when you add outliers. Just like the linear regression example I gave you when you had outliers. In the context of Kalman filtering, by default, the filter is not robust to such outliers. If you do wrong association, that can cause divergence in the extreme cases. In the context of optimization, we have more options. Maybe when we formulate the least squares, we turn it into an M estimator. We talked about wrapping the residual, norm of the residual of the least squares problem around a robust kernel, like Cauchy loss function, right? You remember the idea of having a quadratic loss, and then you use a robust kernel to bend down the size of the quadratic model. We have more options here, and that's exactly what we do. Then we are robust to outliers to some extent, right? We can tolerate some outliers.
What if we already have out of the based optimization? It's not going to be possible.
So now the question is, can we detect outliers and get rid of them? Maybe. It is possible, theoretically. In practice, it depends on what type of inference you're using. The generally topic on outlier detection is still an ongoing debate. But it is possible to separate the process data into inliers and outliers. If you can detect outliers, which is a binary label, right? By definition, something that is outlier is not an inlier. If you can label them and detect them, then you can exclude them. However, how much overhead that process will add to your problem, that's the question. If you go after, let's say, a typical optimization formulation, that will end up being a mixed integer program, which is expensive to solve. You're not going to have real-time SLAM by solving a mixed integer program. You might want to do Bayesian inference. You can do variational inference for defining some latent variables to label outliers. Again, that makes it expensive, right? If you can do that and do it fast, you should be rich. So we won't label them as outliers. We just make the least squares robust, right? I'm telling you about the standard way. There are fancier ways to, again, always build on these algorithms. We should always start from the standard methods that form the core of them.
This kind of scene is associated with some existing part of a map, right?
Map or previous images of frame, two options, right?
So how does it find an existing part of the map which might be associated with this scene? Is it like a search, or does it look for
That's another good question that I was waiting for it, is that, well, in theory, it makes sense that to go ahead and establish loop closures, and everybody is happy. But in practice, where to start the search? There are so many previous nodes and history. You might have thousands of nodes and locations in the map that you can look for establishing loop closures. Just searching for every frame to find all possible loop closures, that's combinatorial, and that will exponentially grow. So that's a big problem in practice. So That's where a map come in. If you have a map and you know roughly where you are, maybe you limit your search to that neighborhood. You have to make some sort of decisions based on sensors, the range, the type of problem you're dealing with, right? There are tuning and design choices of that neighborhood that you want to search. If you have higher level information, semantic knowledge usually help with data association, right? If you, for example, have some notion of block-wise segmentation of some outdoor area, and from your image, you know what area, region you are in, right? Or indoor. For example, you know this is a classroom. And in your map, you have classrooms. You're not going to try to establish a constraint with the cafe and the classroom. So this higher level of information in form of semantic abstraction can help with that a lot to make the search more efficient.
You said before this, so this is good for directing and where is the direct when you are doing an equation. But what if it's an entire loop and you come around the same position after an entire loop?
What if we, now the question is, what if we come back to the initial pose after a long time?
Yeah, then it won't be.
That's the biggest loop you can close. It's the best loop. That's really good because now you go after a long time. Large loops are better than small loops. Maybe I can point out that, again, all of them, if they become different instances of the same framework, but generally speaking, instead of temporal frame, maybe you have some landmarks as well, right? You keep re-observing these landmarks. Now, but it's still you're operating in a window. This is still odometry, although you have local loop closures. So the local loop closures, it's a loop closure because two different poses observe the same landmark. We're not going through calculations of them, but you can always convert them into pose-pose constraint. Geometrically is possible. So the local loop closures you see here, it will certainly help to improve this local tracking. But to really have a full SLAM system is that when you go after a long time, you really need a loop like this. You go around a building, you come back to the same spot, and you establish this large loop closure. That's where we expect to enforce more consistency into reconstruction. Without that, you might still expect some drift, right? Because even a small, why is that? Because, well, you do well in local window, but it's still, unless if you do perfectly, there's a tiny error. And different windows with tiny errors, you really need this large loop to get rid of those tiny errors getting accumulated across time, right? It is impossible to do perfectly in practice using noisy data, right? Does that answer your question? Kind of. Which part of it is not answered?
I was just thinking, my question was, if you come back around after an entire loop, the drift would be so much that if you are going to search nearby nodes, there might be none.
Okay, that's a good question too. So now, the question is that, this is also important, if I'm relying on my current estimate to search a nearby in the graph for loop closure, and it's taking a really long time to go around a building and come back, if the drift is so high that this node is not falling into the neighborhood of this node, right? What can I do? Now, that is a problem if you only rely on your estimate for detecting loop closure, which is why some papers do that, although they get successfully, they get really good results on some data set, but it's generally not a sufficient idea. You do need a way to detect loop closures without relying on your estimates. Visual place recognitions help with that, and they can solve the problem. Because if visually you recognize that this is the same place, you first detect it, and then you go ahead to establish some geometric relationship. So the detection is somewhat independent of your current guess, because it's a visual context you see in the image. One successful method is bag of words, right? Bag of visual words. So you convert each image to a histogram, a visual word, and then you make a library of them. And then you, for every new image, you compare it against the library to see which of the previous images match that. If it's a match, you are seeing the same area from a different, possibly, view. Then you can try to establish a geometric relationship between nodes that correspond to those images, right? So very, very good point, and that is a big problem in practice. So you have a lecture by, a dissertation by Cynthia from last year on visual place recognition. It's on Canvas. All right, so let's formalize it a little bit. I think now you're comfortable with the idea of graph, nodes, edges, loop closures. There are different ways to build that graph. The graph can be directed. The graph can be undirected. One particular choice that is very convenient for modeling in graphical model is called a factor graph. We build the example, and then we say, what is a factor graph? You have your robot here, and then you have the landmark in the environment. Suppose you have your camera can detect the object and it will tell you 2D or 3D position of this landmark. So the measurement model, the constraint that you can add between the robot, your sensor and the robot and the chair, we show it using this model. You can use circle or you can also use square. There's no difference. And you can use a variety of sensors for these constraints. Now the robot moves, the odometry will give you another type of measurements. And we're going to visualize it again using a model. There's another landmark. The robot moves again. Now you see the same landmark again and again as you move forward in the environment. Now at this point, this is a graph, but it's a particular type of graph. Because now you can see that all the table and chair, and we can't visualize all the possible landmarks, right? So we abstracted in the graph as these nodes. So the nodes are the same. The color is just to show you that greens are landmarks here. You don't have to use different colors. And the purple nodes are the robot poses. All the edges are called factors. These factors are measurement models. To make it more concrete, for us, every measurement model is the residual in the least squares problem that we defined. It is a relationship between these variables and your measurement. And this is called a factor graph. It is called a bipartite graph because you can partition the graph into two parts. One part are the nodes, the variables, and the other parts are the factors, the measurements. The factors and the nodes. Now, is there any limitation what type of factors I can add to this problem? No? So as long as I can come up with a way to use that sensory data to establish a relationship, a model, and define that residual between my state variables, I'm good to use it. So I can add virtually unlimited amount of information to this graph to improve my state estimation. So it's a very powerful framework for fusing or combining information from multiple sensors. However, it is model-based, right? So we require model for a sensor to describe the relationship between the variables. What about loop closures? Likewise, loop closures are just constraints between non-temporal nodes. As you can see here, maybe we use cameras to detect loop closure between nodes that are far apart using maybe visual place recognition. So that's all you need to do for formulating your SLAM problem graphically. Once you have this, what type of information you can read from this? It's important you're able to read this. Is there anything confusing here when you try to read the graph?
When you close the loops, do you do anything to, I guess, use the landmark observations, or because the graph says?
Question is, when you close the loop, are you using landmark information or not? We can. There is no limitation. So you can, maybe that was the example of point cloud registration. That will give you directly post constraint. Or maybe you are observing the same landmarks. However, when you observe the landmarks, right, and the landmark itself is part of the variable, it is a loop closure, but it's indirect. The constraint between poses is not directly encoded in the graph. It is via the landmark, right? Because now x1 and xn-1 are correlated via L2. If you marginalize L2 from the graph, then these two get connected, right? There is a way to marginalize it, and you can do that. By doing that, all the edges that are connected to that landmark get correlated.
So, like in this graph, if there's a loop closure between xn and x1, we're assuming that at xn you observe the landmark that, or a place that x1 you also observe. So is that also going to be present in the factor graph?
Maybe landmarks. It doesn't have to be via landmarks. That's my point, right? Maybe this is somewhat abstract here, but maybe it was via landmarks. Maybe you use deep learning to just detect this is the same place. So you can use deep learning based place recognition as well, which is an interesting development, and we want to see where it goes, and hopefully we can use it. Although the generalization is a challenge again to different domains. Maybe you have a way to detect this is the same place, and then you have to establish a geometric relationship such as C2. This can come from a variety of algorithms. Image registration, point cloud registration, maybe it's end-to-end again. Maybe the same deep network can give you a pose as well by feeding it to the similar image. So there's no limitation how you do it as long as you have this constraint. But it's very specific what type of constraint you get once you define your variables. If it's SE2, it is not abstract that this constraint must be also some sort of SE2 measurements between two poses. It's a relative transformation. Okay.
So if we're talking about a closure constraint, it cannot just only come from lemma, but also, for example, odometry measurement will be part of that.
Right. This is coming from odometry, U1. Loop closure does not come from odometry, right? If that was your question. The loop closure comes from perceptual sensors, sensors that can reobserve a reference. A landmark is a reference. We can reobserve it. Odometry, by counting steps and wheel rotations or integrating IMU, will not give us some reference that is reobservable, right?
Okay, what if we have two sensors? For example, one is using camera, the other using a LiDAR, but they have different kind of the collection sequences. Then basically you can use this kind of loop closure. For example, a LiDAR have 10 hertz on that, and camera will have 60 hertz to collect the pictures. So they still have can put it as the loop closure, right?
So let's break down your question. We might have multiple sensors. These sensors are heterogeneous. We might have LiDAR, camera, IMU. They operate at different frequencies. And all of them are challenges. Because you need to decide when you place a node, and based on what frequency, if the sensors are coming and operating at different frequencies, that might be a problem that we're going to talk about it next. Again, in abstraction, there's no limitation. In practice, that's an excellent research topic. How do you solve place recognition problem using heterogeneous set of sensors, LiDAR, camera, maybe proprioception at the same time, because you might sense the roughness of the ground using IMU, although it's not enough. We might add something based on the type of ground you're navigating on. How do you use all of these sensors to solve the place recognition problem better? Don't have an answer? That's a good research problem. I mean, good enough to do a PhD on it, right? Probably we will see more and more papers on this topic in the coming years, because deep learning now allows us a way to process heterogeneous signals and combine them into a latent space representation. Otherwise, it's difficult to turn IMU signals, for example, and point cloud and images into a set of features that are sufficiently useful for something like this. All right, so once you know how to build this graph, and in general you can have as many sensors as you want, there are different variations of the problem. One famous problem is bundle adjustment. Bundle adjustment historically studied in computer vision community. It is a problem similar to SLAM, but you have a single camera. If you have a single camera, typically you don't have odometry. Although you could get visual odometry, but bundle adjustment is not formulated like that. You try to reconstruct an environment as a set of features and camera poses at different time steps. So all you have landmarks, and hopefully you reobserve these landmarks again and again, so you establish edges between different nodes. And then you have the camera poses at different time steps. So there is no odometry edge. This is called bundle adjustment. So you can easily also formulated within this factor graph framework. By the way, nobody's asking what is this hanging there. You all know that? Homework 7 is working. It's the prior, right. So, made my life easier by getting you started early. Okay, so prior, why do we need prior? I mean, it was important enough that it is here. If it wasn't important, we could just not having it, right?
Otherwise, you want to know closest relative to each other, not where any of them are in the global space.
Perfect, yes. So otherwise, everything is relative to each other. If everything is relative constraint, how can we solve the problem with respect to some reference frame? Although there's no universal reference frame to discover, but wherever we start, that can be a reference. That can be 0. So it's necessary to anchor the graph by placing a prior. This prior can be 0, 0, 0, for your pose, and a very tight covariance to make sure it's not moving around. This prior will make the problem well defined. When you form the linear systems, now you can solve it. Otherwise, the whole world will rotate and translate. Everything is relative. So the prior is very important. Sometimes you see even there's a prior on the first 2 nodes. Theoretically, it's not necessary, but sometimes you see the problem is hard to solve, and you have information, then you may as well place more priors. So prior is important so that we have a reference. Another question. Is everything is relative? Can I have, what type of factors I can have? All we see here are factors that are connected to 2 nodes. I want to have examples of factors that are only connected to 1 node, or factors that are connected to 3 nodes. Is that possible? GPS. So if you have GPS, that will be a unary factor. Because GPS is telling you your global position at any time. It is not a relationship between 2 variables. It's just for that time. What is the example of non-GPS unary factor? Depth sensor. Well, depth, you need the map. You need a landmark or some reference. But yes, the depth, if you talk about height, and you know that's your reference, yes, but one of them should be fixed, right? What if the height is changing? The vehicle is also moving up and down. Gyroscope. Is it? Gyroscope is we integrate between 2 orientation. Magnetometer. It is a correction of your orientation with respect to a reference, right? I guess, yeah? Suppose we could. So magnetometer. For legged robust forward kinematics, if you are just having your contact point, your leg point in the variable, and then you always get the relative pose. So basically, that will give you the height of your leg with respect in the body frame. So it is possible. You can, depending on the problem, you might want to think outside of the box. It's not just wheel encoder, IMU, and camera. What is a tertiary factor? That's something that these factors are called binary because they're connected to 2 nodes. What is an example of a factor that is connected to 3 nodes? You see it less because it gets complicated. You want to have a good reason for that.
An example that we're seeing in our project is like Sonar, for example, doesn't create scans as quickly as LiDAR does. So, for example, one full rotation might take 20 seconds. So if you're keeping track of poses over time, you have scans that beams that correspond to the same scan over time. So you have to either stitch them together and combine into a single state, or you just keep track of constraints that correspond to the same scan that you're going to later on use for matching, but are collected at different states. So you have to, there's a couple layers to it.
So Sonar data, when you need to delay establishing the connection. So I'm going to generalize that. When you need a delay we need to delay constructing that constraint, you might wait until you have more observations. The consequence of waiting is that you need more variables in the graph to establish that constraint, because you're also tracking it over time, what variables are seeing more. So if you delay that, if the definition of the factor requires some delay, then you might end up having more nodes. A simple example is when you need to triangulate a feature, maybe using a stereo camera or monocular camera, to have good initialization of the features by observing it from multiple views. You can do that, and that tends to make the estimation better. The Sonar example is good. I think in underwater, that is done. So it's possible, right? It doesn't have to be binary. The sky is the limit. You can model in any creative way you want. So we like this generality of the framework and its flexibility. So this is a very cool problem. You have a lot of fun examples and reconstruction in Visual Islam. You can search to learn about its history and how people solve it these days. But typically, it's a graph optimization solver. OK, so now you learned how to model the problem of sensor fusion for a state estimation as a factor graph. The question is how to solve it. Now, you are familiar at this point with GTSAM or another library that you might have used in your project, G2O, for constructing this graph and solving it. So it is nice to have these libraries. Your concern is building the graph and modeling it, not implementing the solver. However, it's good to understand how these libraries approach the problem for solving it so efficiently. So what's the barrier here? Look at this slide. Tell me how we get from there to least squares. The winner get to leave the class. Early dismissal. You don't need to be here. All right, so to keep it fun and interesting, we're going to talk about this next time. So next time, I want to write down how I can write this factor graph and get the overall objective function, and under what assumptions it ends up being a least squares. So we want to write down that and walk you through it. because if I tell you it's not as good as writing it down. This time, you have to accept that under certain assumptions, this graphical formulation will boils down to a nonlinear least squares problem in the same sense that you've seen before when we modeled the RGBD camera. Yeah?
This guy was talking about the grassland, so I was wondering what would be the motivation to perform this approach compared to the Parker filter approach and the filter approach.
The question is, what's the motivation for this graphical modeling as opposed to particle filtering or Kalman filtering? The filtering, which is part of today's lecture in the end, to summarize, is the problem of estimating your state at only the current time, whether it's the particle filter or Kalman filter. This smoothing framework is the problem of using all the data you have to estimate the entire history, trajectory, at discrete time steps that we track. In filtering, you are relying on the current guess to linearize, for example, extended Kalman filter. What if the linearization is not accurate? So we go ahead and we incorporate information as much as we can, and this process will continue. There is no chance or opportunity to go back in time and correct past mistakes, linearizations. Likewise, in particle filtering, that's not possible. Although particle filter is multimodal and more powerful in some sense. In this framework, we are constantly optimizing the entire trajectory based on information we receive at future times. Because I'm solving a nonlinear least squares problem, and I'm looking at the entire trajectory as in my entire state, right? So this is the fundamental difference. Does this part make sense? Okay.
Is it practical that the accuracy would be better?
So on the surface, you see that, okay, it allows us to correct past mistakes, right? Now, it's very easy to think that, well, Kalman filter is probably faster because I'm just estimating one state. And this is a SLAM, right? We're talking about estimating landmarks and robot pose. You need to track the map. So you need to track the landmarks, or at least a subset of landmarks in your state, but only track your latest pose. Okay? That will be EKF SLAM, or particle filter SLAM. In this case, we are tracking the entire trajectory and also the map, the landmarks. It turns out it is slower to do what Kalman filter is doing. Why? Because when you get rid of history, I excluded that slide. I thought you're not going to ask. So I'm going to draw it. So it turns out when we marginalize history, it makes the problem dense. We lose the sparsity. Whereas when we keep the history, it keeps the problem to be sparse. Because the number of landmarks can be large regardless of number of poses, we end up with solving a dense problem. So you have these landmarks, you have these poses, right? And you have these landmarks, right? when we solve the least squares problem, when we form the Jacobian, this Jacobian is a sparse matrix. When you marginalize it in filtering, what we get is so to marginalize, I'm going to make them black. So this last one is active, right? In filtering, we're marginalizing the history. Now, everything with everything gets correlated as a consequence of. Now, this is proven, right? You can do the marginalization, which is not very difficult to do. You have to do it in the information form, in the inverse covariance form. When you marginalize the history, these are the factors that we removed, it causes the problem to become dense. This graph, in some sense, becomes fully connected because everything is now correlated through the latest robot pose. That's the only thing we're tracking. That should be correlated with everything else. Otherwise, it doesn't mean anything if they're in this state, right? Now, it turns out that this is a bad idea because if the problem is dense and you're tracking thousands of landmarks, it is extremely expensive to solve this problem. It's computationally cubic to solve a linear system that is dense and so large. However, the sparsity allows us to, as you can see here, when we formulate the least squares problem, the Jacobian you see here, the blue dots, are the only points that variables are connected through the model. When I say dense, I mean everything is non-zero here, right? You will never get a real-time SLAM system. There's a scalability issue. This was the knowledge discovered around 2004, 5, 6, 2004 and 5. So since then, basically everybody gradually switched to graph SLAM. So this is sparsity, and maintaining a sparsity requires to maintain the history. That's why that's the main difference. So it is faster and better because we can correct past mistakes. Somewhat counterintuitive.
Maybe that, like, when you described about the problem of dense, it seems like you described that specifically within the graph framework if you were using filtering. But it seems like there are other SLAM methods that use filtering that won't suffer from that problem because you're just throwing away past data, or you're like not looking at all of the landmarks at once. So like, for example, in ROB 550, we do real-time SLAM particle filter. And that is like pretty easy to implement and doesn't have the problem of like taking like n to the 3 amount of time because you're only observing like the thing, or you're only comparing their pose against the things that you can see, not all landmarks that have ever been seen.
Yeah, so the comment is that there are SLAM methods that perform the marginalization. However, they work with a subset of landmarks or maps, and they perform well. And the example you're giving is fast SLAM, particle filter-based SLAM in occupancy grid mapping. Now, that tends to work well because it is in 2D and in a flat ground. Nobody dares to run that on a quadrotor or in 3D SLAM, visual SLAM, right? We yet to see somebody is doing 3D and aggressive visual SLAM or other sensors using that method. So it's a very contained and limited algorithm to that educational setup in the lab that you were talking about, right? It's good for indoor experiments and some indoor environments when you're dealing with flat grounds. I think it's a good algorithm. But it doesn't solve the general problem that we're interested in, right? Besides, it's not really allowing us to efficiently incorporate more sensors to make it better. It is a very specific method of using a particle filter and occupancy grid map. However, I want to connect that to the idea of denseness slam because we're talking about landmarks. The map can be a dense reconstruction of the environment. That 2D occupancy map is an example of that. The densest slam is also an ongoing research. It's an interesting problem. So how can I localize and also reconstruct the environment dense or in a sufficiently complicated way that I can see the scene that I'm observing using my, let's say, cameras? That is a more challenging problem. Although, again, the solvers are using graphical construction for that problem as well. Here we are talking about landmarks as a standard example of it. So another natural question that you might ask is, what's the relationship between these matrices and the graph? The sparsity of this graph, the sparsity of the least squares problem and the graphical model. It turns out there is a one-to-one correspondences. What we see in the linear algebra, although it's linearized, you can formulate the linear problem to see the correspondences, that the graph structure is exactly describing the fill-in that you see in this Jacobian matrix. Because it shows the connectivity of your variables in the sense of linear algebra using matrices. So that was another discovery that they are all related, whether you use linear algebra, graphical models, they are showing the same thing in different languages. So that's encouraging. So we are, next time, we'll see how to get the nonlinear least squares problem. If it's nonlinear, we're going to linearize it, of course, solve it using Gauss-Newton or Levenberg-Marquardt or any other methods that we discussed. And of course, you know that you can form the normal equations. If your Jacobian matrix is a sparse, and there's a lot of zeros, when you form A transpose A, it's also sparse. This is your information matrix, inverse of the covariance matrix. So we have to do a sparse QR or a sparse Cholesky factorization for solving this problem using forward and back substitution. So we will not use QR factorization that's for dense matrices, because then you pay the cost of the full factorization. And this is supported in many languages, but one particular library that handles this is SweetSparse. SweetSparse provides a range of sparse linear algebra methods for larger scale problems, including sparse Cholesky and rank 1 update for your factorization. So if you have this idea of full bundle adjustment and slam, still the graph will grow, right? This is nice to have, and it has advantages over filtering, but it's still as time passes, you will add nodes, and this will quickly becomes intractable because you have so many variables. Even though it's a sparse, that's not sufficient. So one idea to solve this problem is the idea of keyframes. What if you drop some of the frames, still you keep the history to maintain this sparse structure. We drop some frames and only use keyframes, frames that seem to be important. So once you deal with keyframes, the problem becomes more manageable computationally. How to detect keyframes depends how you use to establish factors. Maybe it's using camera, maybe you detect overlap. Maybe if the overlap between some previous keyframe is falling less than 30% or 40%, you initiate a new keyframe. If you're moving faster than certain speed, maybe you trigger new keyframe. Maybe there's a time limit on how far it's been since the previous keyframe. That's another condition you start a new keyframe. So a range of conditions probably usually is used together to decide when to add a new keyframe. So having too much data is a problem, actually. So keyframe idea will make it tractable. Another problem is, well, we can construct a graph and we can solve the least squares in batch. This makes it offline. If I have to solve the problem every time from scratch, that's not very efficient. So the natural question is, can I solve it incrementally by reusing past information? Now the answer is yes, you can. And that's the algorithm called Incremental Smoothing and Mapping, iSAM, which is the iSAM solver in GTSAM. In the linear case, it's exact. If you're dealing with linear systems and you don't have to relinearize, when you factorize your matrix, this R, using your, let's say, QR factorization, when you add new rows to your Jacobian, right, obviously, we're going to have part of this matrix that is not going to be upper triangular. There is a way to update this factorization one row at a time to zero out everything below the diagonal. And that's the problem of incremental factorization. Sometimes it's called rank 1 update of your factorization. But again, we want to make sure we are maintaining the sparsity of the matrices. That's the condition. So it's possible to do it. If it's linear, you can do it exactly, and you can update this in constant time. It means every time you do this, you just need a fixed budget. It's not going to grow as you add more rows. So that's good news. And a particular algorithm that is used is called Given's rotations. There are several algorithms for QR factorization. Given's rotation forms Q matrix, your orthogonal matrix, as a sequence of rotation matrices. So at any time, you just need to apply a new rotation to correct the previous factorization to zero out the most bottom row, right? So I'll give you an example of this code, how it's done, so you can see it if you're interested. So that's good news, and it's constant time. That will make it incremental and online. Now, somewhat bad news is that, well, in practice, the problem is not linear. Assuming the previous linearizations are good enough, we can keep doing this. At some point, we might want to relinearize. So at some point, you need to pay the cost of doing some batch correction. But this still, it's very powerful and enables incremental solution to Islam. For example, if you have 21,000 variables, you cannot possibly handle 21,000 variables in a Kalman filter. It's just the idea of manipulating them in a Kalman filter is terrifying. Whereas this modular framework is way more friendlier than a filtering framework for constructing this problem. So if you have 21,000 variables, if the matrix was dense, you had to store 1.7 gigabytes. Filtering would make it dense. If it's a sparse, you only store 1 megabyte. So the gain is huge. And this was a milestone in Islam, using a sparsity to solve the problem. So that's it for today. Next time, this was for giving you an overview of the factor graph and what's the story. Next time, we want to write down the factor graph, show that how it reduces to least squares problem, where does the sparsity come from, and more discussion on actual calculations. These are good references to read, and that's the end of the lecture.